Does this make sense to everybody? There are two locations of potential interest, okay? One is the end of the plate, because that's probably where the value of x is the largest, so h is the smallest. And if h is the smallest, this guy peaks up. But there is also the point where there is a difference in the expressions for h, because of the fact that the flow goes from laminar to turbulent, and so one has to calculate and see at both these locations where things are changing. Okay? So let's do that step by step. 5 more minutes left. So at obtain Ts. First things first. This is at the edge of being turbulent. So I'm still going to call it as laminar, so that the value of h is still going to use the laminar correlations. Okay? So this is then h is nux times kf by x critical. This is at x is equal to x critical. Substitute for nux. This is now laminar, so put a small subscript L here. And so h becomes the following. 0.453 times the Reynolds number at x is equal to x critical is just the critical Reynolds number. So 5 times 10 to the power 5 to the power 1 by 2. 0.701 to the power 1 by 3. 0.0284 divided by 0.86. Call this as H1. Bear with me for 2 more minutes. This is at the first location. Then I have the second location where I calculate H, and then eventually I calculate the temperature. At x is equal to L. So H at location 2, so this is location 1. We know that at x is equal to L, the Reynolds number is greater than the critical Reynolds number, which means that I have to use the turbulent correlations. So this is nux turbulent kf by L at x is equal to L. Or if you just want to leave it as x, that is also fine. Eventually you substitute x is equal to L for all of them. Okay? Substitute 0.031 Prandtl number to the power 1 by 3. The Reynolds number at x is equal to L, so this is not the same as the critical, it's more than the critical. So 10 times 1.5, 1.725, 10 to the power minus 5 to the power 4/5. Do not forget, that makes a huge difference. Multiplied by kf. All of this divided by 1.5. And I have the answers for these. Very last minute. So H1 is 9.4 meters per Kelvin, degree Celsius, nobody gives a damn. It's all temperature difference. This is 29.5. Our suspicions were greatly mollified by the fact that, of course, the convective heat transfer coefficient is larger when the flow is turbulent, and I just want to recall the following plot. This is as a function of Reynolds number. This is H. laminar, and this is in turbulent, and this is, nobody knows, as the transition region. Nobody wants to touch that as well. There is nothing that is good about the transition. So when you reach turbulent flow, the value of the heat transfer coefficient increases, as is evident from this plot here. And then if you calculate Ts, very last minute, sorry for going a minute above, I'll quit soon. Ts, T infinity plus dq by h, this is 1250, and this has to be, yeah, that's it, 1250 watts per meter square. H, substitute for H1 and 2, so T at T1 ends up being the following. Huge difference. 158 degrees Celsius, 43 degrees Celsius. What a drastic change. So laminar flow is not necessarily always good. Okay? It may be good for fluid dynamics, it may not be great for heat transfer.